In this video, we're going to be covering the SN2 mechanism in organic chemistry. So SN2 stands for substitution nucleophilic bimolecular. Substitution means that we're going to replace one substituent with another. Nucleophilic means that we're going to have an attack by a nucleophile, which is a substance that is electron rich. And bimolecular means we need both our nucleophile and our substrate in order to do an SN2 reaction. If you look at E1 or SN1, they start just with the substrate when it turns into a carbocation. But here, we don't have any carbocation conversions, no intermediates, so we need both the nucleophile and the substrate. So before we look at examples, let's look at the general formula for this reaction. So we're going to have our nucleophile, which for SN2 is going to be a negatively charged anion. And we're also going to have our hydrocarbon with a leaving group. And what's going to end up happening is a substitution with the nucleophile and the leaving group. It's called the leaving group because that's the group that leaves. So we're going to see our products being the nucleophile with our hydrocarbon plus our leaving group separate. But let's take a deeper look at that. So let's start with one of the simplest nucleophiles and one of the simplest hydrocarbons that we can do. So for a nucleophile, we can use hydroxide. It's a strong nucleophile, strong base. It's perfect for SN2. And for our R group, we're going to want something that's not sterically hindered, which means if you think about it in 3D, you don't want there to be a lot of groups attached to it that can block an attack. So a perfect example of this would be to use a methyl group. So if I draw it out, hydrogen is not that big. So eventually, what we'll see in a couple minutes is our hydroxides able to go through the hydrogen to get to that carbon. If we had larger groups, if we had a tert-butyl group attached here, there would be a lot of steric hindrance. There'd be a lot of methyl groups in the way. And even though our hydroxide is small, there's going to be so much steric hindrance from all the electron activity, it's not going to be able to go through. So for this example, we're going to use just a methyl group, and then we're going to use a halogen as a good leaving group. So we can just say bromine. What's going to happen is if I draw out our electrons, we're going to see an attack from the backside. So backside is essentially just meaning the opposite side of where our leaving group is, and that's because there would be steric hindrance on the side with our bromine. Bromine's a large atom, so the side with bromine, there's going to be a lot of electron activity, and it's going to repel that hydroxide. So it's going to come in from the opposite side. And then we can draw a transition state for what this would look like here. So the electrons from the hydroxide are going to start to attach to our methyl group. So we can draw our OH and then have like a dashed bond here with our carbon. Now, this is going to push our hydrogen more towards the other direction. And then we're going to have another dotted line showing that our bond with bromine is going to break. Now, this is going to be a partial negative, and we have another partial negative here. So our bromine is going to get closer to a full negative, and our already negative hydroxide is going to get closer to neutral. So this is our transition state, and it's only here for a short amount of time because it's very unstable. But what we get as our product is we're going to get our OH group attached to our methyl group now. And then we're going to have our bromine separately as an anion. So this is the general mechanism of an SN2 reaction. So we touched on it a little bit, but let's go more into depth on the key features of what makes an SN2 reaction. So the most prominent thing is that there's a backside attack, which we saw in our last example. So our leaving group is going to have electron density around it, and there's going to be some steric hindrance, so it's going to repel whenever our nucleophile is trying to attack. So instead, it's going to do 180 degrees and attack from the complete opposite side, as that's where there would be least steric hindrance. Now, if our carbon is chiral, that'll result in an inversion of our configuration called the Walden inversion. So anything that was wedged, you would make dashed. Anything that was dashed, you would make wedged. The second feature is that it's only a one-step reaction. Even though there's a 2 in SN2, that's just telling you how many different factors needed to start it. So you need both the nucleophile and the substrate to start it, but it's only one step with our very quick transition state. The third thing is that it goes faster the less substituted the carbon is. So what we saw was with a methyl group, there were no substitutions at all. All we had were our hydrogens. That's where it would happen the fastest. So our methyl is ideal, and then we would have our primary, then our secondary, and then tertiary substituted carbons cannot undergo SN2. There's too much steric hindrance. They will go most likely E2, but they will not go SN2. The fourth thing is that SN2 prioritizes strong nucleophiles and polar aprotic solvents. So what's a strong nucleophile? Well, a nucleophile has an excess of electrons, or it's willing to give its electrons away. And a strong nucleophile will be much better off if it does give those electrons away. So these are going to be your anions. So for strong nucleophiles, you want to look for a negative charge. You also want to look at what solvent is in this reaction. So polar aprotic solvents are going to be solvents that don't have the possibility of hydrogen bonding. So if we see some solvent that has an OH or an NH, those would be protic because they have the capability of hydrogen bonding. Hydrogen bonding is not good for SN2 because if we have our solvent molecules, they might distract our nucleophile. Our nucleophile might want to hydrogen bond with the solvent rather than attacking our substrate. Now before we continue, since it's an SN2 reaction going off of our feature number 2, I want to talk about the rate law. So the rate law, we're going to need our nucleophile and also our substrate, making it bimolecular. Let's look at this example. This is sodium cyanide with a primary halide. So we know it's a primary halide because if we look at our central carbon that's attached to the chlorine, there's also a methyl group that's attached to it. Now, if you remember from the last page, a primary halide is still okay for SN2. There's a little bit of steric hindrance from that additional methyl group, but we still have our 2 hydrogens. There's still enough room for our nucleophile to go in. But now let's look at our nucleophile. So we have sodium attached to cyanide. When these break up into ions, we'll have our Na plus and our Cn minus. So the cyanide is going to be the nucleophile here. So if we take the cyanide and we draw the arrow going to the carbon, we see that we have this DMSO where we have our arrow from reactants to product. DMSO is dimethyl sulfoxide. This is one of the most common polar aprotic solvents that you see. So the fact that we have a polar aprotic solvent here just helps us even more understand that we're going through SN2. So let's draw our transition state. We're going to have our cyanide, and we're going to draw our partial bond to our alkyl halide, and then we're going to do another partial bond with our halogen, with our leaving group. Now if we want to draw our charges, our cyanide was a strong nucleophile, it's an anion, so by putting it in a partial bond with our alkyl group, it's getting closer to neutral. It's not completely neutral since it's a partial bond, so we're going to give it a partial negative. Well, our chlorine is getting closer to a full negative charge when it was originally neutral. So this is also getting a partial negative charge. Once this transition actually happens, we will be left with our cyanide bonded to our primary halide. Now this is not a chiral carbon, simply because we have two hydrogens here, so we don't have to worry about any inversions. But if we had another group, if this were secondary and we had another group instead of one of the hydrogens, we would want to make sure to essentially flip all of our wedges to dashes, all of our dashes to wedges. Let's look at this example. So now we have sodium hydroxide. We know our hydroxide is going to be the nucleophile. And now we have a secondary alkyl halide. We have two CH3 groups here. This is going to be slower than our methyl group, slower than our primary that we saw, but it's still possible. It's just going to be at a slower rate. What we're going to see is the lone pairs, one of them, on our hydroxide group is simply going to backside attack once again. A DMF is dimethylformamide. That is another common polar aprotic solvent. So if we draw our transition state, once again, we're going to have our hydroxide with a partial bond with our two methyl groups attached. Another partial bond with our bromine. And these are both partial negatives, once again, with our final product being the OH group attached to our alkyl halide. Also, we're going to have our bromine anion. Let's look at an example where we do have a chiral carbon. If we look here, we have 2-bromobutane. This is in the S configuration. We're going to have, again, our hydroxide electrons attacking. This is a secondary carbon, so it's going to be a little slower, but we know it's still possible. Once again, we're going to have the electrons from our hydroxide do a backside attack. Our bromine has a wedge down at the bottom, so our hydroxide is going to attack from behind it, so we have the least steric hindrance. What this is going to do is it's going to invert all of our groups. If you think of this in 3 dimensions, if we have our bromine pointing out towards the screen, that means that our hydroxide is going to be back against the screen. I'm going to skip the transition state here because it was the same for all of them. But what we're going to have as our product is we're going to have our hydrogen, which was on a dash, now be wedged. And since the stereochemistry does matter, it's stereospecific, our hydroxide group is going to be the one that is now dashed. So we can put that on the dash and then draw everything else just like normal. And then we would have our bromine anion as well. If this video did help, please consider liking and subscribing. If you want to see a comparison with SN1, E2, and E1, I will have the video linked in the description. Thank you for watching.